Today is the last lecture of structure analysis content. So I hope you guys are gonna have good Thanksgiving by the end of this week. And next week we are gonna have our last week to wrap up the class. We're gonna have on Tuesday the presentation. Every team is gonna have 15 minutes, 12 minutes to present, 3 minutes of questions. As I said before, you guys have to show me how's your structure look like. You need to show me the relationship between the properties of the structural elements with respect to the results that you have, like base shear, shear lag, story drift, total displacement. I need to see all these things. You know, when you extract the figures for the inter-story drift for the structure, how the profile of the structure look like and how the drift look like. So I need the screenshots from ETABS with all the results that you have, and definitely the shear lag at multiple stories. You can, I don't know, like if you're building a 60-story, maybe you pick story number 1, story number 10, story number 1, 11, 21, 31, 41, and show me how is the shear lag in the earlier stories and in the top stories look like. And definitely this is for the multiple models that you have. Okay. All right. So that's, I believe, everything about the presentation next week. Yeah.
You said Tuesday, but last time you said Thursday.
No, we said.
So.
Oh yeah, the presentation is Thursday, right? So yeah, sorry about that.
Okay, no, just making sure.
Thank you. So okay, so Tuesday we are gonna have the exam, and I'm talking about the Thursday, which we're gonna have the presentation. For the report, you don't have to submit it on Thursday. You can submit it the week after. I believe I put a deadline. I'm gonna open a panel on Canvas with a deadline for the whole submission. You have to submit a presentation. You have to submit a Word file for your report and a PDF, and these has to be separate. And then a zip file with all the runs and the analysis that you have done. Please don't send the report with the analysis, okay? Make the report separately in a separate file, PDF, Word, along with the presentation file that you have, okay? You guys got that? All right, so for the final exam on Tuesday, the final exam is gonna have the topics after the midterm. I'm not gonna test you the topics before the first midterm. So the topics that we covered the springs stiffness. We covered the flexibility method, the method of consistent redundant, and we started last time stiffness method for trusses. And today we are gonna do some, I wanna say, introduction to stiffness method for beams. We're not gonna cover it all because we don't have time, but I'm gonna give you some introduction how to develop or how to find out the stiffness matrix for a beam. I'm gonna teach you some stuff, so there's a question definitely at least from 35 to 25 points on the lecture today. So we are gonna have one question springs, one question flexibility method, one question trusses, and one question on this lecture. Okay, so I'm telling you all, probably 5 questions. Okay, like today maybe 2 questions from the lecture today that they are gonna add up to like 30 points or something. Okay. All right. So if you guys remember the stiffness matrix, this is actually the general rule of stiffness is coming from like the Hooke's law. So we have the stiffness K multiplied by delta, right? This is the general rule that covered the whole thing. We were able to convert this simple rule to a much bigger one, that the F nodal forces equal to the F fixed end forces plus the K multiplied by D, which D is also a displacement vector. This is a stiffness matrix. This is a fixed end force vector, and this is a nodal forces. By the way, B here equal to the F nodal forces minus the F fixed end forces, and it's gonna be a symbol, right? So we just expanded the whole thing because this one is very simple. If you are only dealing with 1 degree of freedom and axial stiffness, this is not gonna work if we have much bigger structure. So that's why we needed to expand the rule and come up with the stiffness method equation. This is the general equation. And all our mission was to find the nodal forces, which is a direct forces at the node. It's given, it's a load at the node, which means at the degree of freedom. Okay? Fixed end forces is a forces coming from other load affecting the degrees of freedom. Like, if you guys remember, we had something like this. And if I'm looking, I have a degree of freedom U1 here, this one. And I give you a nodal force directly at the node, moment M is equal to 2 ton-meter. So that means this is a nodal force, a direct load at the degree of freedom, so I can put this here. But what if I have a load here? This load is gonna add some load to the degree of freedom, so that's why we get the fixed end force component, okay? And we explained all this. So I just wanna talk a little bit about the stiffness matrix here. This is the stiffness matrix of the structure. Like you can remove K, but the same rule apply for elements. Like I can put this S. The thing is, if it's element, if we are gonna convert these two elements, so that forces at the member is also equal to the fixed end forces plus the stiffness matrix of the element multiplied by U at the elements. All right, so it's also the same thing, all right? So we need to talk a little bit about the properties of K. What is the properties of the stiffness matrix of a member? Number one, the number of columns, it's a square matrix equal to the number of columns, rows, sorry. Equal to the number of degrees of freedom. So if you have 2 degrees of freedom, so it's 2 by 2. If you have 3 degrees of freedom, it is 3 by 3. If you have 6 degrees of freedom, it's gonna be 6 by 6. That is the stiffness matrix of the structure. So that means it's a square matrix. Number 3, it's a symmetric matrix. Which means the off diagonal elements are equal. So if you have your matrix like this, and this is the diagonals, all the members here, all the elements here equal to all the elements here. That is the symmetric matrix, which makes it like the T inverse. The inverse of this matrix is equal to the transposition of this matrix. Okay. Number 4, the diagonal elements are always positive. Number 5, element stiffness matrix is a singular matrix. So if you look up this term, singular matrix or singularity in structure analysis, singular means unstable. And that's actually makes sense because if you guys remember, when we developed the stiffness matrix of a member, that member was free, wasn't stable, it was in the air, assuming that all the nodes has degrees of freedom. So that means this member is unstable. If I lift it, it's gonna fall on the ground. When this member is not gonna be stable once you fix the some degrees of freedom. And when that happens, when you put this member in a structure. So that's why we call it, it's a singular matrix. Singularity means that we cannot get the inverse of the matrix. By the way, so this one apply for that's why we usually get the transposition. So it means we can't get inverse of the matrix. And why is that? Because the determinant of the matrix is equal to 0. The determinant of the stiffness matrix or a singular matrix is equal to 0. And I'm sure you guys have studied before how to get a determinant of a matrix, right? Okay, so let's actually forget about this and talk a little bit about how we can, I'm just like giving you guys this to understand. If you have a matrix and there's numbers here like on the diagonal are not positive, negative, that means there's something wrong. Like if there's numbers that you got here is negative, it's not supposed to be negative, it's supposed to be positive. If a number here doesn't match the number here, that means there's something wrong, okay? So let's actually have an example. Develop a stiffness matrix of frame, because we did this for the truss last time. We are gonna do it today for a frame. So frame element stiffness matrix. So for a frame element stiffness matrix, first before I get the stiffness matrix of a frame element, do you guys remember how many degrees of freedom that the frame element has? 6, right? What are they? So I have U1, U2, and U3. That is 2 translation, 1 rotation on one end, and then another on the other end. So this is U4, U5, and U6. How about the truss element? Do you guys remember how many degrees of freedom? It's 4, 2 translation at one end, and other 2 translation and at the other end. Okay, so let's actually develop the stiffness matrix of this member. But I want to talk about the, by the way, this is 6 degrees of freedom, but it has 3 types of stiffnesses. What are they? It has normal stiffness, shear stiffness, bending stiffness. So if you want to find the normal stiffness of any member, you try to extend it. Add 1 unit deformation, find the forces, you are going to find the stiffness. If we want to find the shear stiffness, apply unit deformation that way and see how much forces you need to make a unit deformation. Why? Because the definition of the stiffness is force per unit deformation. Apply unit deformation and find the force. So that is the stiffness. Bending stiffness, try to rotate your member with 1 unit rotation and find the forces that is developed. That is the stiffness. And that's what we used to do to find the stiffness matrix of a truss member. So let's get them one by one. Let's, number 1, get the normal stiffness. Okay, you tell me, the normal stiffness is related to which one of these degrees of freedom? U1 and U4, right? Okay, so if you guys remember the steps that I had in previous notes, how to develop the stiffness matrix of an element, first, you have to fix all the degrees of freedom. Don't let them all move. And then apply unit deformation, add the degrees of freedom of interest. And then find the forces that needs to move this degree of freedom. So let's do it one by one. So first, I have to fix all the degrees of freedom. So that's my member. And I'm gonna fix all the degrees of freedom. And by the way, I'm not gonna make this intermediate hinge because right now this is not a truss member. Let's make it solid point like this. And I'm gonna make this solid point. And I'm gonna fix all the degrees of freedom. None of them is gonna move. And then I'm gonna apply unit degree of freedom. Add the degree of freedom of interest, U1. I'm gonna make U1 equal to 1. By the way, and I said that before, the normal stiffness is independent from the shear and the flexure stiffness. What does that mean? Like if you put a unit displacement in this direction, it's not going to develop shear and moment. It's just only going to develop tension and compression. But if you put unit displacement shear, so the shear is going to develop shear and moment. So shear and moment are always coupled together. If you apply shear, moment is going to develop. If you apply moment, shear is going to be developed. But if you apply normal force on this member, you are not going to have shear or moment, right? Like if I have this member and you put force like this, is there any shear or moment on this member? No, it's only compression. There is no tension, there is no shear. Like here's my member, like this. But if I put shear, so there is gonna be shear and also bending moment. If I apply rotation, there are gonna be shear and bending moment. That is one of the characteristics of these stiffnesses. So if I apply U1 equal to 1, so there will be only one force in this direction. Why? Because to make a displacement here, you have to have a force in the direction of the displacement. And then you have a reaction on the other direction, right? And we agreed last time that this is equal to K and K is equal to EA over L. We proved that last time, if you guys remember. We did this, we said that B equal to K multiplied by delta. And we used B, we said that the force B is equal to the stress multiplied by the area, and this is K and delta from the strain equation, delta over L. That's the strain is equal to delta over L. So if you want to put delta, is going to be epsilon multiplied by L. So K is equal to sigma A over epsilon multiplied by L. And we know that Young's modulus is a stress over strain. So we can remove this and we put EA over L. We did this last time. That is the axial stiffness of any member. And by the way, this is going to be the reaction on the other side. We can prove this using the flexibility equation. Like we can get the forces outside using the flexibility equation. You can get it in many ways, but let's do it actually using the flexibility equation. If you guys remember, if we want to solve a structure, indeterminate structure, we choose a main system, right? Like this. This is the main system, and this main system needs to be determinate and stable. All right? So what forces that I released here? I released the shear, I released the normal, I released the moment. However, I'm sure that the shear and moment are equal to 0 in this problem, right? There's no shear, there's no moment. So I'm not interested in these two, because I know for sure that these two are equal to 0. So basically, I can only account for this force, the normal force. So what we used to do to solve these kind of problems, we used to, this is the main system. We are going to call it NO, the normal force O. And we make another system, which we call it the virtual system N1. And we put a unit load at the displacement of interest. So if you guys remember, I'm looking for a unit load in this direction, so I put 1 ton in this direction and get the normal force. The normal force is going to be equal to negative here, -1 and -1. This is the main system. This is the virtual system. By the way, the main system doesn't have any original loads, because the main system that I have here only have displacement. Let's say if it has original loads, maybe it can have distributed loads, it can have concentrated load. I'm gonna put them here, but it doesn't have any original loads. So the normal force on this system is equal to 0, because it doesn't have any original load. It only have displacement. So what we used to do after that, we need to substitute in an equation, NO plus N1. Not this one. We used to substitute in an equation equal delta 1O plus F delta 11 equal to delta. Do you guys remember this equation? We need to find delta 1O, and since this is a normal force problem, we integrate N1 with NO dl over EI, and we use the triangle table to get this. And delta 11 is the integration of N1 dl over E. Sorry, this is EA because the normal force doesn't have I. EA and we get this value. By the way, you integrate 0 because there is no original load here with a value, so 0 with a value is going to give you 0. There is no delta 1 ohm because there is no load normal force here. How about integrating this with itself? Integrating this with itself is going to be 1 over EA, and if you look at the tables that you have, you integrate triangle with a triangle, it's going to give you 1 by 1 multiplied by L. So this is going to give you L over EA. Try to look in the table 1, the one that you have, and see integration of a rectangle with a rectangle. So basically it's going to give you 1 multiplied by 1 multiplied by L, which is the value here multiplied by the value here. And by the way, both of them are negative. Negative and negative is going to be positive, is going to be L over EA. So here's my equation. I know for sure that delta 1O is equal to 0. This one is 0 because there's no external load. I want to get F. I want to get delta 1, sorry, I already got delta 1 here. By the way, we usually used to put delta equal to 0. Why? Because if you guys remember, I told you before, let's say that this is my structure and I have this, and I usually delta here is equal to 0 because there's no delta allowed here. But if you have this as a spring, there is delta, right? Here, I already give you that there is delta equal to 1 here. So it's a pre-existing condition that the delta at the point that I'm interested in already have delta equal to 1. So basically this delta is equal to 1. So I can solve the equation F delta 1, which is L over EA, equal to 1. So F is going to be equal to EA over L. So the force here that we are looking for is equal to EA over L, which is the same one that is here. So you either find it with the Hooke's law and also the stress-strain relationship, or you can find it with the flexibility method. All right, so basically right now we were able to find the forces here and here. So in the exam, I will ask you a question like this. There will be a question like this one. It can be normal stiffness, it can be shear stiffness, it can be bending stiffness. I'm gonna tell you, find the fixed end forces from a unit deformation U1 equal to 1. So once you solve all this, at the end you are gonna write this. You are gonna say that the fixed end forces from U1 equal to 1 is gonna be equal to, you are gonna open a vector, and this vector is gonna have the force at U1 is gonna be EA over L, and then U2 and U3 doesn't have any fixed end forces, 0 and 0, and then number 4 has negative EA over L, and then 0 and 0 because there's no forces in the 4 and the 5th direction. So this is the fixed end forces that is going to be generated if you apply a unit deformation U1 equal to 1, or if you want to find out the normal stiffness. So this is the normal stiffness of a frame member. Did you guys get that? So why I put them in this arrangement? Because these are the fixed end forces corresponding to each degree of freedom. Degree of freedom U1 has EA over L, U2 has 0, U3 has 0, U4 has negative EA over L, U5 0, U6 is 0. Okay? Alright, so let's do the same thing and try to find the shear and the flexure stiffness. Okay. Shear stiffness, number 2. By the way, if I ask you that question, like find this, you're not going to use this one. You are going to use, I'm going to ask you to use the flexibility method, the same way that I have done it here. Okay, for shear stiffness, here's my frame member. It's something like this. That is degree of freedom 1, U2, and U3. Same thing here, U4, U5, and U6. And shear stiffness, that means that means either U2 or U5. That's what the shear stiffness that we're looking at. So that means I'm gonna fix all the degrees of freedom, and I'm gonna apply U2 equal to 1. What does that mean? That means like your member is something like this. So, and all is fixed, I'm gonna hold this support and move it by unit displacement and try to find the fixed end forces that is gonna happen. It's like your structure like this and try to apply a movement and see how much forces you're gonna have. All right, so let's see how we can solve this. The thing is, if you have a shear force, it's not gonna generate normal force. Normal force, it needs a normal straining action, need a normal force to be generated. So I know for sure that there is no normal force is gonna be generated from this one. The only way to generate a normal force if you have a large deformation like that. We are telling me that you are gonna take this whole thing all the way up, very, very long, and elongate it. That means they're essential. But we use the small displacement theory. Like all our displacement is within a few centimeters. So that means it's not gonna be enough, or even millimeters. So it's not gonna be enough to generate a normal force. Okay, so normal force is 0. So all what I wanna find out, if you apply U2 equal to 1, how much shear force you are gonna have here, and why did I put this force up? Why didn't I put it down? Because the what?
The self-weight of the beam.
No, we are not talking about self-weights. Like all this, we are assuming that the self-weight is 0. Like there's no self-weight in this the thing. The thing is that this force is going up because there's definitely no way there's a displacement is going up and the force is going down. So the only way to get this displacement all the way up, there's definitely a force taking it all the way up. Like, okay, this went up 1. Definitely there's no way that this force is gonna go down. Since this went up, that means that there's an external force take this point up. Alright, so this is the only way to happen. So if this force is down, that means there's something happening. There's a problem. Why? Because actually this force is the diagonal, the one on the diagonal. And we said that the diagonal elements are always positive. It's coming from this rule. Like look here, we put U1 is that in that direction. That means that the force that drive U1 is in that direction, in the same direction of the displacement. Okay. All right. So I'm gonna tell you something else. If the displacement is going up like this, that means that the moment is something like this. This is the direction of the moment. The tail of this arrow is with the direction of the displacement. And here, the moment also is something like this. They both are in the same direction. And to balance this, definitely the reaction here is gonna go down. Why? Because these two moments wanna flip this beam that way, the other two is gonna make a counter moment in the other way. Our mission right now is to find the fixed end forces for the 4 of them. How we can find it, we will find out right now. All right, so we are gonna use the flexibility equation. We are gonna pick a system that is determinant and stable. So I'm gonna make this system something like this. That is the easiest system that I can pick. A fixed cantilever, something like that. And my forces that I wanna find is F1 shear and F2 moment. I want to find F1 and F2. You can call this M2, but let's say them F1 and F2. Let's find these two forces. If we found these two forces, we can find the reactions at the end. So since we have two unknowns, our equations are something like this. Here, we have only one single equation because it was only one force. But here, our equation is going to be something, if you guys remember, delta 1O plus F1, delta 1, plus F2, delta 1, equal to delta 1. Delta 2O plus plus F1, delta 2, plus F2, delta 2, equal to delta 2. Do you guys remember these two equations from the flexibility method? You have to remember these. We put them in a matrix after, like it was something like this. Delta 1O, delta 2O plus a matrix has delta 1, delta 1, delta 2, delta 2, and then you have F1, F2, delta 1, delta 2. We did this like 3 lectures ago, all right? Okay, so we need to find these deltas. So if you guys remember, the only way to do this, I have to do this system 2 times. One like this, and one like this. And I put unit load at F1, so I'm gonna make F1 here equal to 1, and a unit moment 1 ton meter. And try to find the bending moment for both of them. This is the main system MO. It has 0 bending moment because there is no external loads. Because my beam doesn't have any load, but if my beam has some loads, there's gonna be MO. So M1 and M2 is gonna be something like this. This is gonna be positive moment, and if the span is L, so it's gonna be 1 multiplied by L. That is positive bending moment. For the 1 ton meter is gonna be negative, and it's gonna be something like this. -1 and -1. That is the bending moment for the unit loads. So since we have MO is equal to 0, so all these vectors are gonna be equal to 0. Like delta 1O is equal to 0, delta 2O is equal to 0. Why? Because basically delta 1O is equal to the integration of M1 MO dL over EI. And MO is equal to 0, so everything is going to be equal to 0. Alright? Okay. So let's get delta 1, delta 1, 2, and by the way, delta 1, 2 equal to delta 2, 1. I told you there's a rule, it's called Maxwell-Betty reciprocal theory, that delta 1, 2 is equal to delta 2, 1. Try to get it, integrate this with this, or this with that, so it's the same thing. Alright? You're going to use the same triangles in the table, it's going to give you the same answer. And then the last one is delta 2, 2. So this is going to be the integration of M1 dL over EI, and then you find the number, the integration of M1 M2 dL over EI, and this is the integration of M2 with M2 dL over EI. So once you solve these,
So this one does have EI instead of EA?
yeah, EI, because that's a flexure stiffness. EA is only if you are looking for axial stiffness. All right, so you're gonna find out that delta 1, 1 is equal to L cubed over 3 EI. Delta 1, 2 negative L squared over 2 EI, and delta 2, 2 is L over EI. So basically you are going to solve 2 equations and 2 unknowns. You are going to have something like this, a matrix, L cubed over 3 EI, negative L squared over 2 EI, negative L squared over 2 EI, and here is L over EI. And then you want to find the value of F1 and F2, and you tell me, what should I put here? Delta 1 and delta 2. Delta 1 is the initial deformation in the direction of force number 1. Delta 2 is the initial deformation in the direction of F2. What is the value of delta 1? Is equal to? What is the initial deformation in the direction of F1? All this is coming because we have U2 is equal to 1. We have 1 in the direction of F1. So here you have 1. But there is no deformation in the direction of F2, rotation, so this is 0. Okay? So I have 1 and 0. Why? Because the initial deformation at F1 is equal to U2 equal to 1. So I have to solve this. Once you solve it, you are going to find that F1 is equal to 12 EI over L cubed, and F2 is equal to 6 EI over L squared. So that means, let's say what this means. If this is my member, and this member is fixed, something like this, and you hold the one end, and you apply a unit deformation at this end, U2 equal to 1, the forces that is gonna develop from this deformation, you need a shear force here that is F1, which is this one, is equal to 12 EI over L cubed. And then the moment that is gonna generate it here is 6 EI over L squared. And the moment that is gonna be generated here, how can I get it? Basically, you can take the moment here. Take the moment here around this point and try to find how much moment you're gonna have here. So you are gonna find out that this moment is equal to 6 EI over L squared in this direction. And you can find the sum of Fy equal to 0. You have to have a force here equal to 12 EI over L cubed going down to balance this force. Okay, so this beam is balanced. How? These two moments, if you plus them together, is gonna give you 12 EI over L squared, right? Because they both are in the same direction. And these two are making moment equal to 12 EI over L cubed multiplied by the length of the couple, which is L, so it's gonna give you 12 EI over L squared. So this is the final fixed end forces. By the way, I took this in the 3rd year of college, and I still remember these forces. I have to remember them, because that is the stiffness matrix of this member. I know that it's gonna have 6 EI over L squared here, and there's a 12 EI over L cubed here. And at the end, you have to write this vector. By the way, if you solve this and you stop here and you didn't write the fixed end force vector, you're gonna lose some point. I need you to say that the fixed end force for U2 is gonna be equal to 6 numbers. The first number is the force in the degree of freedom 1, which is 0 because there is no force in U1 direction. And the force in U2 is 12 EI over L cubed, and the force in the U3 direction is 6 EI over L squared. U4 is 0, and then this one, these two are negative. No, this one is negative. U5 is equal to 12, negative 12 EI over L cubed, and it's negative because it's in the opposite direction of U5. U6 is positive, 6 EI over L squared. That is the fixed end force vector. 6 numbers for 6 degrees of freedom. All right? Okay, did you guys got that? You need to understand how I did this step by step. That's the 25 points in the final exam. Okay? All right, I'm gonna do the last one. Do it over there. Do you have a question? Anybody? By the way, the flexural deformation is the same thing. Like, let's say number 3, flexural stiffness. Okay, so this is my member, has 6 degrees of freedom. So I have U1, U2, U3, U4, 5, U6. So I'm going to do the same thing, fix all the degrees of freedom, and then apply unit degree of freedom, add the degree of freedom of interest. Right now I'm interested in U3, so I apply unit deformation. So I hold the support and try to rotate it, theta equal to 1 radian. So in the positive direction of U3, so this is gonna be theta equal to U3 equal to 1 radian. So I wanna find out what is the reactions that is gonna happen on this if I rotate this support. I'm sure that they are gonna be shear force here and a moment in this direction. Why? Because there is no way that you are gonna have this rotating that way and the forces applying the other way. The deformation always happens in the same direction of the force. There is no way on earth that you would push this with a force 10 and this body's gonna go in the other direction. You push it that way, it's gonna go that way. You have and the opposite is the same thing. If this body is moving that way, that means the force that applied on this body is in the same direction of the displacement. So if this theta is rotating that way, that means that the moment is in that way. All right, so to do this, we are gonna do the same thing. We are gonna pick a system that is determined and stable, and the best system for this is a cantilever with a free end, something like that. That is the main system, and we are gonna get MO for the system, which is 0, because there's no any applied forces, it's only displacement. And then I'm gonna apply unit deformation at the redundant force. I have 2 redundant forces here, so I'm gonna do the same thing. This is F1, and this is F2. So I'm gonna apply 1, and then I'm gonna apply 1 ton-meter here. It's gonna be the same like this problem. It's the same thing. You are gonna find the moment. It's gonna be 1 multiplied by L, and here it's gonna be negative, -1, and -1, something like this, negative, and this is positive. All right, so, and this is 0. Delta 1O equal to delta 2O is equal to 0, and then you are gonna get delta 11, which is gonna be equal to the same one that is over there, and delta 22 is also equal to the same one because it's the same triangles. You are gonna find out right now what is gonna be the difference. Delta 12 and delta 21, also we can find them. So we're gonna end up with the same matrix like this and the same forces like this. The only difference is gonna be this vector. So I'm gonna put the matrix here, the one that it was over there. As far as I remember, it was 3L over EI.
No, L cubed over 3EI.
Okay, L cubed over 3EI. This one was negative.
L squared over 2EI.
Okay, L squared over, it's negative, right?
Yeah.
Over 2EI, and here negative L squared over 2EI. I'm sure I'm gonna get this one right, L over EI, right?
Yeah.
Okay, so this one, and I wanna find F1 and F2. Can you guys tell me what should I put here? This is deltas. I wanna find the delta at degree of freedom 2, and delta at degree of freedom 3. 2, there's nothing at 2, so this is 0. But there is rotation at degree of freedom, so, and this rotation is equal to 1. This is the only difference. This becomes 0, and this becomes 1. All right, then you will find F1, and then you will find F2. And as far as I remember, when I was in 3rd year college, I think F1 was equal to 6 EI over L squared, and this is equal to 4 EI over L. Yes, 6 EI over L squared and 4 EI over L. So here, we're gonna put this something like this. This is my structure, and we applied unit deformation like this, and the forces that is gonna be developed here, 4 EI over L, and this one is 6 EI over L squared, and definitely here is gonna be 6 EI over L to balance this force, and here is 2 EI over L. How did I know that? Take the moment here and find the moment that is gonna balance this moment. So get summation Fy, summation Fx, you are gonna find the forces here. We usually say if there's a concentrated moment here, this moment is gonna carry down moment here half the value of the moment over there. There's some rules for that, but let's say try to take the moment here. Taking the moment here, 2 EI over L and 4 EI over L is gonna give you 6 EI over L. And this one is gonna counter couple 6 EI over L squared multiplied by the span L is gonna give you 6 EI over L. So the fixed end forces for this problem, F for U3, can you guys tell me what should I write in this vector? 6 numbers. 0, 6 EI over L squared, 4 EI over L, 0, negative 6 EI over L squared.
Positive 2EI over L.
Excellent. That is the vector. So this is the vector. We got it for 3 degrees of freedom. The thing is, we do all this to find the stiffness matrix of the member. So we got it for 3 degrees of freedom. We can do the same thing here. But by the way, if you did the same thing here, it's gonna be exactly the same like here. Like let's say actually, if I have the same one, I'm gonna do only one example. I'm not gonna do for all the 6 degree of freedom. And the thing is, I applied a unit degree of freedom in the direction of u6. That means that you added degree of freedom like theta here is equal to 1. All right? So what this means, to make a theta equal to 1 here, that means you need a moment here equal to 4 EI over L. And if this is down, that means that the force is going down. If this is going up, so the shear force is going up. So this is gonna be 6 EI over L squared if you solve it, okay? And here is gonna be 6 EI over L squared. And since this one in this direction, so you are gonna have 2 EI over L, sorry, this one. Something like this. How can I solve it if in the exam I told you find the fixed end forces due to u6 is equal to 1? You are gonna do the same thing, but rather than freeing this end, you are gonna free the other end. Like your system is gonna be something like this. And this is your forces, F1, and the moment in this direction, F2. And try to find them. Once you find them, it's gonna give you something like this. You guys tell me, what is the fixed end force for u6? Based on these forces. 0. 6 EI over L squared. 2 EI over L. 0.
Negative 6 EI
Over.
L squared.
And then
4 EI
4 EI over L. Excellent. So we have this for the 6 degrees of freedom. Okay, let's write the stiffness matrix of.
So the only thing that switches is the moments?
The only what?
The only thing that like swaps is the moments?
Yeah, because the thing is, the moment the theta happened here, so this is where the 4 EI over L happened, and this one is 2. This one, this is where it happens, so this 4 EI over L is here. The thing is, there's a rule in a structure analysis. Let's say I have a structure like this, and I applied concentrated moment here, let's say 100. If I apply concentrated moment 100 here, there's a moment here is gonna be developed is equal to 50. It's gonna throw off half of the moment. All right, so let's write the stiffness matrix of the element. So K, definitely it's 6 by 6, and it's gonna be a big stiffness matrix like that. And I'm gonna divide it to 4 quarters, and all right, so each row or column in this matrix has the fixed end force vector that we got. All right, so let's write them one by one. So do you guys remember the one that was here, the normal stiffness U1? This is for U1, U2, U3, U4, U5, U6. If you guys remember, it was EA, and then 0, and then negative E over L, because there was EA over L, and the other one here, 0, 0. Excellent, that's U1. By the way, if you do the same thing for U4, and applied U4 in that way, so it's gonna give you U1 in that way, negative EA over L. Like if you did the same thing here, and you put U4 equal to 1, so that means you're gonna have EA over L here, and EA over L here in the negative direction of U1. So this, if you wanna get U4, it's a negative EA over L, 0, 0, EA over L, 0, 0. And that actually applies to the rule that all the diagonal element is positive. So EA over L, and this is supposed to be positive. Why? Because the diagonal element represents the forces in the direction of the degrees of freedom. Like U11 that means the force in U1 direction. U22 is the force in U2 direction. Okay, all right, we got U2. Do you guys remember this one? Can you guys tell me what? Actually, let me do it myself and see if I remember. Okay, remember it was 0, 12 EI over L cubed, 6 EI over L squared, 0, and negative 12 EI over L cubed, and then 6 EI over L squared. That was this one. U3, the one for shear, was 0, and you have 6 EI over L squared, and then 4 EI over L, 0, negative 6 EI over L squared, and then here 2 EI over L, right?
Yeah.
So that is the one. This one comes from the shear stiffness, and this one is the one that we wrote here. By the way, this is number 6. We can put it. You can put here 0, 6 EI over L squared, and then you are gonna have, I believe, negative,
No.
No, it's positive.
positive,
Wait,
2 EI over L, and then you are gonna have 0, negative 6 EI over L squared, and then 4 EI over L. All right, so this is this one. And by the way, there's actually a rule that tells you this one is supposed to be this one, but the off-diagonal metrics are negative. Like if you take this one and you put it here, so this is gonna be equal to negative 12 EI over L cubed. All right, so this one is the same thing, but the off-diagonal matrix is opposite sign. Can you see this negative 6? Here's 6. This one is 6, so you're gonna have negative 6 EI over L squared. And this one is equal to this one, but the off-diagonal matrix is in opposite sign. So this one is gonna be 0, and this one is gonna be equal to 0. So this is this 12 EI over L cubed. This is 6 is positive, so it's gonna be here negative 6 EI over L squared. So that is the stiffness matrix of a frame element. So if this 4 quarters, let's say this is 1, 2, 3, 4. 1 is equal to 2, 3 is equal to 4, and off diagonal element is in opposite direction, opposite sign. All right, you want to prove that? Look at this. This is equal to this. EA 12, 4, EA 12, 4. Negative 6, negative 6, positive 6, positive 6. This one is equal to this, same diagonal. Negative EA, negative 12, 2, negative EA, negative 12, 2. This is positive 6, negative 6. Here is negative 6, positive 6. So if you found the 3 degrees of freedom, you can find the other ones. That is the degree of freedom of the stiffness matrix. By the way, solving a beam problem I'm just gonna give you an idea. I'm not gonna solve it. How to solve a beam problem. Same thing like we did with truss. Like let's say that you have a beam like this, and this beam is fixed, hinged, and fixed. How many degrees of freedom this structure has? Is there any degrees of freedom here? Here? Is there any degrees of freedom here? It's only 1, so you only have 1 degree of freedom U1. So at the end of the day, when you build the structure stiffness matrix of this structure, it's gonna be equal, S is equal to 1 by 1, right? Because it's only 1 degree of freedom.
Can we call it U3 or because
This one?
Yeah.
This is a structure of degree of freedom, not element degree of freedom.
Okay.
So if it's element, if you are gonna take this everyone its own, you can put this is equal to, and by the way, this is not gonna be U3, this is gonna be U6 for this member and U1 for this member. You know, because this is at the end of this and this is at the start of this member. But this is a structure stiffness matrix. So actually your equation is gonna be equal to F nodal forces, F fixed end forces, plus S multiplied by U. Okay? All right, so what I wanna say is is the same concept. You are going to build the stiffness matrix of this member and the stiffness matrix of member number 2. This is K of member 1 and this is K of member number 2. 6 by 6, K1, and this is 6 by 6 for K2. And look at the degrees of freedom where it is. There's no degrees of freedom here. All of them are zeros except this one has U1, right? Because that's the first member. Has the degree of freedom rotation at the end. This one has 0, 0, U1, 0, 0, 0. So all these are zeros like this except U1, but you have to do the same thing here. 0, 0, U1, 0, 0, 0. Here, all of them zeros except U1. So you have to cancel all these. Oh no, sorry. I got so excited. So I only have this one, and I have, okay, we don't need to do the same thing again. So I have this, and that. So I only have this one. So basically, S is going to be equal to, look at that, it's going to be equal to 4EI over L from element number 1 plus 3, which is 4EI, another 4EI over L from element number 2. These two that come from the element number 1 and this comes from element number 2. And by the way, if I give you in the problem that this has EI and this has 2EI, sometimes I give you different stiffness. So basically, number 2, rather than having 4EI over L, so you are going to take EI and put 2 EIs. So that's like one of the tricks. I'm not going to give you a problem like this, but I'm telling you this is how you solve the problem. All right, same concept. My question in the exam is going to be on the how to prove that the fixed end forces, how to get it. All right, okay. The last 15 minutes I'm going to spend it with you on things that can make things easier when you solve problems. I'm going to introduce the concept of symmetry and skew symmetry. How can we take advantage if our structure is symmetric or skew symmetric to make the problem get solved faster? All right, symmetry is something, let's say you have a beam, something like that. Let's say I have a beam hinged and has a distributed load like this. What do you think of this beam? Is it symmetric or not symmetric? It's symmetric. Like if you come in the half and take a line, this is the line of symmetry. There's hinge here, there's hinge here. There's the same load on the left and the right. By the way, symmetry for problems, it needs to be symmetric in the loads, geometry, supports, and the inertia, EI. If here has EI and here has 2 EI, that's not symmetric. Needs to be in all of these. Loads need to be symmetric, geometry need to be symmetric, supports, and EI. So, can you guys imagine with me the deformation of this beam, how it's going to look like? The deformation of this beam is going to be something like this, right? That's how the deformation is. Can you guys tell me what is the theta here? 0, right? Because here the line is horizontal at the end. So at the axis of symmetry, there is no rotation. Theta is equal to 0. And this point cannot move left or right because it has to be in the center. Okay, so there's no horizontal movement because if the structure is symmetry, let's say there's a load here and load here. If it's symmetry, this point in the middle cannot move because if this is going to make displacement that way, the other load is going to bring it back. So theta is equal to 0. The u horizontal is equal to 0, but there is u vertical. it's allowed to move up and down, which makes sense, right? Because the point is gonna go down. Skew symmetry is the opposite. What is it? Like skew symmetry, let's say I have a frame like this, and this frame, okay, you tell me, if I have this load that way and this load that way, what is this? That's symmetry, right? So if you take line in the middle, all the loads left is symmetric with the load on the right. But if this load is going to the other direction, this is called the skew symmetry. All right? Same the thing every way, except the load isn't like same direction. That's called the skew symmetry. So that is the only difference. All right? So this is called the skew symmetry case. So what about the skew symmetry case? This actually is gonna move something like this. So basically, in a skew symmetry is the opposite of the symmetry. The U vertical, usually, by the way, this point are not supposed to like go that down, but I'm gonna write U vertical is equal to 0, and U horizontal exists, and the rotation theta also exists. Why I'm saying that? Usually, let's put it that way, just to make it. It's gonna be something like this. It's gonna be something like that. Same thing if you have, for example, a graph like this. If you have this load is 2 and this load is 2, that is symmetry. But if this 2 is going down, that's a skew symmetry. That means if this point is gonna go up because of this 2, it's gonna come down because of the other 2 in the other direction. So we will end up with U vertical is equal to 0. There's only one case. If you have an intermediate hinge here in the middle, there is theta is not equal to 0. I mean, like there's theta is gonna happen if there's only intermediate hinge. I'm gonna give you a few cases that can help you with the symmetry and the skew symmetry. Is okay. Let me put it here. So if I have a structure like this, and I have a structure like that, let's see what is the difference between the symmetry and skew symmetry. The thing is, rather than solving the whole structure, I can take one half and solve this half separately. Like I can take the one here and solve this, and I can take this one and solve this. But the thing is, I need to find a support that can represent the symmetry that I have here. How can I add a support that has theta is equal to 0, horizontal movement is equal to 0, and also allows the vertical direction? Can you guys find me a support that can satisfy these conditions? I need a support that can make this point can move up and down, but in the same way, make this point doesn't move x and y and also restrict the rotation. This support is guided support, like this. But if you have an intermediate hinge here, that means the moment is equal to 0, so we need to release the moment from here, so this is gonna be a roller that way. Why? Because I already know that the moment here is equal to 0. Guided is gonna develop the moment. But if you put a roller is gonna allow the moment, make the moment is equal to 0 to match the moment here, and only allow the vertical rotation. So this is the supports that I put here. So this is I'm gonna write the same thing here. I'm going to talk about axially flexible and axially rigid in a little bit. So here, and then I'm going to add the ruler is that way. All right, So what is the difference between axially rigid and axially flexible? That means that the members are not allowed to have axial deformation. It's rigid, cannot go up or down. So if it's axially flexible, actually it is very easy. That means that I have U1 that way, U2 that way, and this can rotate. And I only have U4 that way, 4 degrees of freedom, something like this. That means all the member can extend, can go up, can go down. But if you have axially rigid member, actually you are not gonna have U1. Why? Because U1, that means that the member is gonna have a compression or tension, and that's not allowed. This is a rigid member. So you're only gonna end up with having one rotation that way and one vertical movement that way. U1 and U2. You'll tell me where's the U1 and U2 here? Where's the translations? The translations are gonna be neglected because this is a rigid member, is not allowed to be extended up or down. Cannot allow to have this. So all the translations are gonna be canceled. You're gonna tell me, how about U2? That's a translation too, but it's not gonna make any of these members to be extended. All right? So same thing here. You are gonna have a rotation here and also rotation here because this is a hinge and you can go up. So it's U1, U2, U3. Here is a flexible member. If it's a flexible, so the same rules are gonna be applied, the one that we learned from before. All the degrees of freedom are gonna be there. U1, 2, 3, 4, and 5. The only special case is the rigid, where we cannot allow the axial deformation. How about the skew symmetry structures? For skew symmetry structures, rigid and flexible. Let's put the same structure. You have fixed, and you have one that has hinge, something like this. Let's see the difference. We need, this is the axis of skew symmetry, and this is the axis of skew symmetry. By the way, I mean like symmetric, that means that the loads are something like this. If it's skew symmetry, that means that the loads are something like this. Okay, for symmetric structure, I need a support that makes UV equal to 0, the vertical equal to 0, and allow horizontal and theta. Can you guys find this? I'm gonna take the half, and I want a support here that can allow horizontal movement, but restrain the horizontal movement and restrain the and allow the horizontal and allow theta. It is gonna be roller, right? The roller can make the horizontal movement allow, can also allow theta, but can restrain the vertical movement. And if you have an intermediate hinge, it's gonna be the same thing because still roller allow the moment, right? Yeah.
But our, load is in vertical direction, so it should move in vertical direction, so should we rotate this?
UV is equal to 0.
This is for not horizontal direction. No.
Horizontal is allowed. This is can allow the horizontal and can allow the rotation, the roller. But U vertical is equal to 0. Doesn't allow the vertical translation.
Okay, but I was thinking that we have shape also on these equations.
We have what?
We have also shape on the right. Yeah, up.
Here?
No, right.
This
Right.
one?
Right up.
This one, yeah.
But it's horizontal. So that's why we allow horizontal.
Yeah, but this one is gonna allow the horizontal.
So he's saying because the loads on that top one is to the right, and the one that we have right now is currently in the vertical rather than the right.
Oh, this one, these two?
Yeah.
No, I'm just like making it up, like it's any loads. But even with these, like let's say you are gonna have a general load, something like this.
Okay.
I'm talking about general case.
Okay.
Like I'm just like making these loads to tell you, because if I put the same shapes here, you're gonna tell me these structure are the same. Just wanna say that this is gonna be skew symmetric, this is gonna be symmetric. But in this case, yeah, it's not gonna move, it's gonna only have a rotation. All right, so same thing if you have flexible structure here and here. All right, so the degrees of freedom that we're gonna have, you are gonna have a rotation here, and you are gonna have a rotation here. And this point, you can add rotation, you can add translation here, if you make the same translation here, like if you make this U1, this has to be U1. They both have to be having the same translation. I'm not gonna get into this. I just wanna show you how the shapes look like, all right? The question that you might get in the exam is gonna be something like this. It's gonna be a small question, have 5 to 7 points. Look, I'm gonna give you, for example, a structure like this. Looks like it can be symmetric or skew symmetric, right? So to be symmetric, loads has to be symmetric. Skew symmetric loads has to be skew symmetric. But what if I give you a load like this equal to 10 and a load like this equal to 12? This is not even symmetric or skew symmetric, but we can convert it into two systems. This is equal to a system like this and like that, hinge and hinge. Look at this. For symmetry, I'm gonna take these two loads, 10 plus 12, and divide them by 2. It's gonna equal to, actually let's make this 14, or actually let's keep it small, no problem. This is gonna give you 22, it's gonna give you 11, right?
Yep.
So 11, that's for symmetry. For skew symmetry, I'm gonna subtract them. 12 minus 10 over 2 is gonna give me 1, right? So what I'm gonna do, I'm gonna put 11 here and 11 here. Is that symmetry or skew symmetry? Symmetry. And look what I'm gonna do. This one, I'm gonna put 1 up and 1 down. So 1 plus 11, if you plus these two together, is gonna give you the 10. 1 plus 11 is gonna give you the 12. This is symmetry, and this is skew symmetry. And then you can divide this from here and put a support, like you can divide this. For symmetry, if you guys remember, we put guided support, right? That's why you have to show me. And here for skew symmetry, we put roller, right? So basically, to solve this problem, you convert it from 2 degrees of freedom to 1 single degree of freedom at the end. You solve this and you solve this. In the exam, I'm gonna ask you, I give you a question like this, you have to show me the two system, you have to cut in the half, and you tell me I have to solve this system and this system. I'm not gonna ask you numbers. I need you to show me the final system. Okay, this also can be, one last thing. Where's the, let's say, for example, I have a frame, big frame, something like this, and I put a distributed load, and I put load 15 and 10, and I put 10 here, and I put 10 and 14. You see this one? Oh, that's either not symmetric or skew symmetric, but the thing is the geometry is symmetry, so there's something that I can do. You can make this one into 2 structures and take them one by one. I'm gonna put the symmetric load, something like this. By the way, this load, the distributed load, is gonna stay in the symmetric part because this distributed load, 2 tons per meter, is already symmetric. It's not skew symmetric. And this is the skew symmetry part that I want to work on. Let's take them one by one. I can take 10 plus 20 plus 15 is 25. So basically, you can divide 25 over 2. It's going to give you 2.5, 12.5, and 12.5. So I can put 12.5 and 12.5. Let's see what we are going to do here. 15 minus 10 is 5 over 2 is 2.5. So I need 2.5 that way and 2.5 that way. 2.5 plus this is going to give you 15, and this one is going to give you 10. All right, we are done with this part. Okay, let's get 10 and 14. It's 24, so it's going to have 12 and 12. And then 14 minus 10 is 4 over 2 is gonna give you 2. So you need 2 up to balance the 12 to make the 10, and 2 down to be 12 plus 2 is equal 14. So we got done with this load. How about the 10? The 10 is a little bit tricky. So what we do is like 10 plus 0 is gonna give you 10, over 2 is gonna give you 5. So you can put 5 and 5, right? And here you are gonna put 5 and then 5 that way. So 5 is gonna cancel the 5, it's gonna be 0, and 5 plus 5 is gonna give you 10. So you end up with having two systems. One of them is symmetry, one of them is a skew symmetry, and actually you decrease the degrees of freedom by a lot by solving only one half of the structure. At the end, I want you to cut this in the middle and take one part and show me what support that you are gonna put here. Since this is the symmetry, I know this is gonna be guided support. And the other one is skew symmetry, is gonna be roller. Something like this. And at the end of the day, I don't want you to solve the whole structure. You can take this half and solve it alone, and this half and solve it alone, and you solve it the whole problem. Bending moment is gonna be the same, shear force is gonna be the same. You just add them together. But at the end, we add these two together, all right? Did you guys understand the symmetry and skew symmetry? I'm not gonna ask you a question to solve the problem. I'm gonna want to show me how is the symmetry and skew symmetry look like. Don't solve, right? Okay, so that's it for now. This lecture is gonna have two questions in the final exam. One on the skew symmetry, 5 to 10 points, and one on developing the stiffness matrix, and then the other three problems on the other three lectures from the last 2 weeks, okay? All right, so see you guys next week, and you guys have a happy Thanksgiving. And if you have any questions while you're preparing the presentation, you can text me on campus, all right? Okay.